All right. Well, today I'm, filling in for, Paul Hauser, and I put these slides together for the last couple of days. Hopefully, I'm going to give you a taste of, the Landsat imagery in managing water resources, in water consumption. I would like to acknowledge a couple of my team members, Dr. Campbell and Ian Radcliffe here, that they contributed a lot to some of the presentation that, I'm going to share with you today. All right, before I actually start my presentation, I wanted you guys to see a time lapse of Landsat on a Google Earth engine. I thought, Greg, you fixed this mouse, but all right, let's see. All right, so here's a Landsat annual time lapse. These are Landsat images going back to 1984 up to 2012. Again, the Landsat archive goes back all the way to 1972, but Google doesn't have the collection prior to on their archive yet. So anyway, here I want you to just get a feeling of what we can get from the Landsat imagery, from this satellite. And here's our, I zoomed in to Lincoln, and this is our O Street. And you look at it, and if we go down, let's see, let's start over here. 1984, over here in southern Lincoln, you can see the expansion in urban area. For instance, here, about 5 years ago, you can see the target was there. Over here, the highway. It's really nice way of, looking at the change in land use, especially in this case, the expansion of urban land in southern part of Lincoln. So it's a beautiful, gorgeous, detailed archive, historical data that we can go back in time and see what was it look like, the land use at the time. Here's, for instance, back in 1984, my house is somewhere here. All right, this is our Holmes Lake, and this is 40th Street. Here's the Yankee Hill. My house is somewhere here. It's all farmland earlier in 1991, 93. And then just right after mid-19s, you can see the expansion, the schools, the buildings. So it's a really great archive, the data set we get from this satellite. I can pause it here. Well, you know that NASA launched a number of satellites, and these are some of these. And the Landsats, the LDCM, the last one is, after successful launch, it's been changed to Landsat 8 over here. That's the last satellite. Today's presentation, really, what I'm going to talk about is the Landsat, these satellites. Right now, we have 2 of these satellites in orbit. Well, why Landsat? Is a natural resources. We need to look at the human impact. What's the impact of the human impact at the scale of at the field scale, and then we can. We name this field scale ranging from meters to 10 meters. As a natural resources, when we look at the phenomena to understand any physical processes or behavior, we really look at the top-down approach. Really look at zoom in at the field scale. That is the human scale that we call field scale, and that is. And the Landsat is the only satellites that provide such a detailed information, the field scale information that is 30-meter resolution going back all the way back to 1972. And some of you might not know that the Landsat program here in U.S. is facing challenges because of the funding issue. The continuity of the program is being really in risk. Again, one reason, because when we design these satellites, the life term, the design of life of these satellites is only from 5 to 7 years, except Landsat 7 and 5. And we have images from Landsat every 16 days, and we might get clouds. So one satellite in orbit is not enough for our natural resources. We need more than one. We need 4 satellites so that we can really mitigate the clouds and really look at the impact of human activities at the field scale. And again, right now, currently we have 2 Landsat satellites, and these satellites are costly. They takes about 4 years to build these satellites, and it costs us $1 billion. And our Congress, the U.S. Congress, is reluctant to spend that much money. And then, but again, this is the archive data set, and we really need to have a solid program looking forward so that we have sustainability of this Landsat and data archive. And we are challenged, and unless you tell the Congress, the people, that you need such scale, you need this data set, we're jeopardizing basically. You gotta tell them what you need. Otherwise, the sustainability of this program will be in jeopardy. And the water resources community was a vocal community in Landsat 8 because for the launch of Landsat 8 for the thermal imagery. They didn't want to include thermal imagery because that adds another $200 million. So the water resources community really put a lot of pressure on Congress, this Western United States, and we got the money, and now we have Landsat 8, and we have thermal imagery. That's what we use for water resources. And, well, you keep hearing from NASA and other people, well, why not use other satellite? Well, the water resources community, not only water resources community, for natural resources application, we really need that thermal band. And most of these satellites, orbiting the Earth, they don't have the thermal band. That's, one dilemma. Second, those satellites who has thermal bands, they do not have the resolution that we want. We would like to go back to the impact of human activities. That is our field scale. That is our 30 meter. And if you look at these models, the new name is VIRS, it's just too large for us to quantify a change in land use. For instance, here, when you look at this color composite for Albuquerque, New Mexico, this is you can see the individual fields, you can see the buildings, you can see the Rio Grande, and you can see the native species along the river. And let's look at the right image, the MODIS. And there's no way you can discriminate this. So, with the MODIS, with such satellites, there is no way we can accurately quantify the change in land use, or to quantify water consumption or expansion of the native species. So that is one reason we want Landsat, and we need Landsat. Again, here's a picture showing how many paths it takes to cover, for instance, in Nebraska. And I brought my globe at home. I figured that, there are about 15 students here. It's good for them to visualize this whole process. So here is in Nebraska. It takes 5 paths to cover the entire Nebraska. If you want to utilize Landsat to do a land use change, versus if you go to Russia, you need 50 plus pads. These are called pads, to cover entire Russia. So it's a really detailed data set, and it's the satellite is a polar orbiter. That means that it's orbiting the Earth from north to south, and when it's orbiting the Earth travels, right? It rotates. So, and each time the Landsat pad takes 90 minutes. So from every time when Landsat makes one orbit, it takes 90 minutes. Another 90 minutes, the second time when Landsat comes, the Earth rotated. So it takes a new path. Again, the Earth, after 90 minutes, the Landsat is back again taking pictures. And again, 90 minutes, it takes another picture. So after 16 days, we get a picture of the same location twice. Because of this, 90 minutes orbiting again and again, it's just that it's not possible to take a picture, every day for the same location. We have to wait 16 days to get a second picture. And the timing of the pictures is fixed. Approximately at 11 a.m., Landsat takes its picture. Right now, with the Landsat 8, we have push broom. Before we had the whisk brooms, Landsat satellite, it was just like a whisk, and now we have the push broom sensor. And 11 a.m. in the morning, it takes its picture, and the sun is up there, watching Landsat, looking over its shoulder. Every 10 a.m. it takes its picture. It's 11 a.m. in Turkey. The Landsat takes its picture. It's 11 a.m. in United States. It's 11 a.m. in China. So 11 a.m. the Landsat takes its picture. And again, every 90 minutes we have a new path. So that's pretty much how the polar orbiting works with satellite. Here are a number of satellites that's been launched, and I didn't include the earlier ones. The Landsat 4 is being quickly replaced by Landsat 5, again in 1984, because Landsat 4 quality wasn't that good. And that is the first time we had a thermal imagery on Landsat satellite. Really, the bottom line here is the shortwave reflective bands has a pixel size. The pixel is like a grid, the definition of ESRI, the grid. It's like a square. It's a 30 by 30 meter. You have one number. And the thermal data, the pixel size, is ranging from 60 meters to 100, 120 meters. The Landsat, the last one, has a 100 meter pixel size for thermal band. And again, we have 2 satellites up in the orbit, 7 and 8. 7 has problem, scan line detectors malfunctioning back in 2003. So we have a lot of holes in Landsat 7, and pretty much right now we're relying on Landsat 8. Well, again, here's a question I thought it would be interesting to ask, why I became interested in Landsat. And here are my options that you can choose from. 1, when I was born, my first choice was Landsat. B, I'm a diehard Star Trekkie. C, my father was a Spock. And D, I love evapotranspiration. The answer is, can you guess the answer? D, yeah, the D is the answer. I love evapotranspiration, and that's why I became interested in Landsat. And those who might not know what the evapotranspiration is, it's really the sum of transpiration from the plant and the evaporation from the soil. And in ET, I'll call it ET from now on, is really needed to produce food. As a scientist, us, we have obligation. We have obligation to increase the food production. There is a demand, and people are dying because of the hunger. More food production means more water. What's that mean? That means we need a better estimate of ET so that we do a better job for global food water production. And that is why this satellite-based ET data is critical. Again, going back to Landsat 8, I didn't even post these pictures on my Facebook, so you guys are lucky to see it. These are the pictures that I took, or some of my colleagues took while I was just posing. The Landsat 8, I was lucky to witness the launch at Vandenberg Air Base in California back in February 11, 2013. This is really the state of, even though they were talking about the data continuity, the Landsat 8 is really the state of the art. We use the best technologies. We use the better radiometric accuracy. Everything is perfect or close to perfect. Again, I witnessed, and there were a lot of emotions going on, with the failure of Landsat 6 and then the scan line detector malfunctioning. There was a lot of anxiety whether this launch will be successful. And it was successful, and I was so happy to be, to witness the launch. All right. This is the Landsat. Here's the satellite, all right? Here's the satellite. Don't worry about the bottom part. That's where they keep those fields. Usually, they keep enough that these satellites will last for 10 years. And then some data logger, if I can find my mouse. All right, here's our thermal. There's a OLI and operational land imaging. That's the sensor that collects the data from the reflective bands, the shortwave bands. And here's the tiers. This is the thermal data. So the satellite has 2 sensors. And believe me, it's costly to have more sensors. It's probably right now, they are saying, is there a way we can launch a small set so that we don't have to put both tiers and OLI together? Again, I thought I should give a good credit to Dennis Ruder, NASA. He's the one developed the tiers. He's the lead scientist. Again, it's a great technology. It's latest technology that uses quantum well infrared photodetector. In Landsat 7, for instance, we had only 8 detectors. And with this Landsat 7, with the Landsat 8, we have 5,000 detectors. Every 30 meter pixel, we have a detector. And he's the guy behind this. And the QWIP has never been used in space technology before. So it's really the state of the art. All right, so what do we get from this thermal sensor? The water resources community is yelling about. We get surface temperature. And here's a surface temperature map for western Nebraska that Ian, I'm not sure Ian is here, developed some time ago. And we can really get a lot of information from this surface temperature. And here are some of the irrigated, like you can really nicely see these center pivots. The temperature is, let's say, ranging maybe 302, something like that. And when you go to rangeland, dry land, temperature is 315 or so. So you can really see the impact of evaporative cooling, by just looking at this surface temperature map from the thermal imagery. And that's the phenomena that we use. We can use this surface temperature, or call it radiometric temperature, to derive the ET. Again, here's the color composite, just some snapshot. This is the data from just the recent satellite, the Landsat 8, showing the center pivot irrigated fields close to clay center. And here's the ET map from this Landsat 8 data, again, using the surface temperature. Again, this is the first ever ET map that's been published and created by the Landsat science team. That was us, the University of Idaho and Nevada DRI, that, March 22nd, the first Landsat 8 image was available, and we processed the ET. Again, we look at the California because it's winter. That's the only place we can see the greenness, the ET, the transpiration. So we were very proud. Well, again, we have these maps, but what is it good for? Again, we can use this to solve some of these potential water conflicts in western state. This is a report from the Bureau of Reclamation. There's a lot of conflicts over water in western state, and we can use this satellite-based information to resolve some of these issues. Again, what is it good for, the ET maps? What do I get out of the ET maps? Again, we have a better understanding of how much water is being used, when it's being used, and what do you think the third one is? How much, where, and when it's being used, right? So we can find out, the timing of we can look at determine the timing of the irrigation by looking at this map. Again, these are every 16 days we have the snapshot. We can find out the timing of the water use, how much is being used, and these are the spacious, gorgeous, detailed data that we can know where the water is being used. So that's the main, takeaway message from these ET maps. Again, in Nebraska, I think the last 4 or 5 years, we're ranked number 1 in terms of the irrigated 8 million acres. Across the country, we have 50 million acres irrigated land. Let's assume everyone sells their water right from those irrigated lands. And the value of these water rights is more than 200 million. So that is why the serious estimates of water consumption, especially in these western states that they are fighting over water, is needed to manage these properties and to manage the water resources. Again, the human activity, people manage the water at their field, right? At the field scale. So that's where the Landsat comes in. These water rights are at the field scale, so we need the field scale information. Well, here in our home, the ET maps gives us information about how much water is being used total from month to month here in Central Platte Natural Resources District. And July and August is really the month that, a lot of farmlands are, these irrigated farmlands are using the water. If you zoom in, we can see the variation even within the field. And when you go further here, there are some roads, dirt roads, something you see less ET. When you go over here, you can, this is really gorgeous, enormous data set that we can get from the satellite. Well, we determine this ET as a residual in the energy balance equation. I'm not going to go through, and we used both CBOL and metric algorithms. Again, these two models are commonly used to, to help with these water rights, water management. And the metric model has been developed at the University of Idaho. I guess I don't know how I am doing with time, but I'd like to, kind of give you a little bit taste of some of the application of metric here, in our home, in USA, in abroad, as well as some of the applications done by our collaborators. Well, Nebraska, again, it's been the ET maps has been used to manage the depletion. That's the whole idea, to manage the depletion to the Ogallala aquifer. I mean, it's really not serious, but when you go down to Texas, the aquifer, is getting the low and the water level. So our natural resources district, the Central Platte, has adopted the use of Landsat really to manage the groundwater depletion and to help them with some of the modeling efforts in the district. Again, here are some. We did 4 years of image processing for Central Platte, again showing, for instance, 2007 ET maps total for the NRD district. Again, tells you where the water is being used. Then you look at it and how much has been used. Look at over here, go back to July. We have almost, over 200 millimeter total ET per month from these irrigated lands. And then there's the timing of the irrigation, so we can get a lot of information. Again, just zooming in, and we can look at the variation in ET from year to year. We haven't done the monthly for 2013 yet, so I have only 3 years here. So the same field here, in 1997, it was creating a lot of ET versus, is slightly lower when you go back to 2007 or 2011. It's a great data layer. Well, every time when we produce these maps, we want to make sure that, we can rely on, it has to be authentic. It has to, you have to have a, you have to have a good confidence. So we've been using Dr. Irmak at BSC's data since 2005, kind of to, compare the model predictions with the observation. We've done this for every year that if this is, for instance, 2011, the predictions match pretty well to measurements. These are the measurements from the Bowen ratio system. Again, here's a application at the Rio Grande of New Mexico by Tasumi in 2005. The Pueblos, these guys, these Native Americans, they sued the state of New Mexico and they sued the federal government because they want their water rights back. These water rights goes back all the way to Coronado when the Spanish explorer came to the New Mexico. So this ET information is being used, to protect these water rights for these Native Americans. Plus, the second common use of the ET maps in New Mexico is really looking at the invasion of the salt cedar or other species along the Rio Grande. It's just, there's a lot of effort to reduce the expansion of invasion species. Another application here's by our colleague at the University of Idaho, again, similar to UNL, producing several years of ET maps to calibrate the mud flow that's being developed for the Snake Plain. Here's the Snake Plain aquifer. That's a common use. in Imperial Valley, California. And, in the last, I'll say 10 to 15 years, the 15% of water supply from agriculture is being transferred to San Diego and Los Angeles to support the city. They need more water. The city is growing and growing, so they're paying farmers to irrigate less so that they can bring more water to the cities. And here's the Imperial Valley. It's a nice area. This area, about 80% of our winter vegetables are grown in this area. So if you don't irrigate, you're gonna see the impact, in your crop production. So the ET maps, again, help us here to determine the impact of water transfer on agriculture area here, also as well as at the Salton Sea. I don't know what's wrong with this thing. It's working, not working well with me. All right, Montana. Here's another flathead, the Native Americans. Again, it's being used to settle the water rights for the Native Americans here, the flathead. Again, they have been, you really need to balance the amount of water that you use for irrigation. Here, these are the farmland. And the amount that it has to stay in the river for the fish habitat. And so the ET maps, again, has been used to settle the fight between these fishermen, the guys, and the Native Americans, so that there's enough water in the stream so that, the ecosystem is sustainable and the fisheries are, doing well. So this is probably something very interested natural resources students here. All right, Wyoming. This was really great. It was the first time we really used that metric ET maps back in November. That's U.S. Supreme Court. And, this is the Yellowstone River. These are the sub-watershed. It's hard to read. Here's sub-watershed. And the water is, going from Wyoming to the Montana. If the Wyoming irrigates a lot of water uses, then there's not much water left, for Montana. Similar to other states, Montana sued Wyoming, and now, they're settling in the Supreme case, and the ET has been, the maps has been used to settle the fight between the Montana and the Wyoming. Again, the border is again flowing from the Wyoming to the Montana. All right, let me see. I hope I'm doing okay, Mary. You can. All right. So another, I thought it was interesting research is really that's what we're doing for the NASA's architecture team is looking at the ET from the different satellites. Well, now we have 2 satellites up in the orbit. If we run our metric, for instance, are we going to produce the same results from both satellites? They're not cloned, let's admit it. They can produce different results. So that was a question that's being addressed by this NASA's architecture team. And we look at the Underfly date. When they launched Landsat 8 in February 11, 2013, there were 2 days these satellites were orbiting only 7 minutes apart. So they're exactly seeing the same location, just 7 minutes apart. So we look at this Underfly region, for the California, because that's where we can see in March greenness, the ET, and this is from Landsat 7. I guess this mount is Landsat 7. Again, because of the scan line detector malfunction, we have a lot of holes, and the quality of the Landsat 8 is not arguable. It's beautiful data set. So this is again the same date. The data is being taken just 7 minutes apart from each satellite. And what we found is really, this is kind of visual comparison, almost perfect fit Again, these are not clones. And, it's just we were so happy to see that. And also, of course, NASA wants to know how good this new Landsat, the Landsat 8. Okay, I mean, it's the state-of-art technology, but, it's always, people in people's mind, how good it is. Are we doing the right thing here, doing the right geometric calibration, things like that. All right, let me introduce you to some of the applications that we did overseas. One is Chile, and here the motivation was, it's not only Chile, it's in Europe too. There's this global expansion of olives and vineyards, and now the natural vegetation is being replaced by these olives and vineyards, and this put a lot of pressure in water resources in Chile. Now you have this olive system or vineyards that you have to irrigate. So you have to manage this irrigation, and they would like to use the satellite data to help them to manage the irrigation. We did a study here in the center of Chile, and these are those olive trees. They're pretty dense, young trees. Again, this is happening in the last 5-10 years. Those natural vegetation, this completely disturbance in ecosystem is being replaced with these, young trees. And our collaborator at the University of Talca, Dr. Samuel Ortega, they were measuring the fluxes, these energy balance parameters, water, with the eddy covariance units brought in olive and the vineyard. So I'm just going to show you some results from the olives. Again, anytime when you go outside the U.S., there's challenges finding the data, especially the GIS data. So they don't have a land use map. We have to work with the global land cover. Also, this is a completely new ecosystem. It's a tree. Look at that tree. There's like 5 minutes apart. These are not corn, soybean trees that the metric is being developed, the agricultural crops. So we have to do quite a bit of modification to improve models so that we can have a good estimate of ET from this ecosystem. All right, here so what we found after, maybe it's a little more tuning here, after calibration, new function, we found a pretty good match with the metric results and the measurements here from the olive. Again, because of the, they take LAI, for instance, a few times. So these are like 2 years data. It doesn't look like it's pretty dense. Again, I was there. I didn't post this in the Facebook too, so you're seeing it first time. I was there back in January, visiting Dr. Ortega and his team members, and I was collecting data at least for 3-4 days out in the field. And one thing that they are actually using is the octocopter. Here's the octocopter. Now this, you can, manually operate, collect data. I can hardly see on my screen here. So, this is like a little tower. You fly at 60 meter high at altitude. The battery lasts about 30 minutes. And you enter your predefined coordinate GPS, and you tell this, tower to go, where to go. And then it has 3 sensors here at the bottom. It has a thermal imagery sensor, and it has one for the shortwave reflective bands. They also put one cheap Canon camera or something. So here's a true color composite, when you take that image from the shortwave. This is 30 meters. So when this octocopter takes an image, takes a size of 30 meters, okay? And this is 1 centimeter at the shortwave, these blue, green, red. And it's 10 centimeters at the thermal band. So, we have this 30-meter Landsat, but we don't know what is going inside it. So this data really helped us to visualize, to understand the behavior of this system, what is going on here in terms of the, the lens surface, the canopy structure. So it really help us. It will help us to fine-tune, the metric model. So now that we have this data, we know the sunlit, the shaded soil, we have the canopy, we can really, help to tune or calibrate, develop a 3D model, for this new architecture. So this information will be very useful for us. Again, it will really help us, this really to understand the pixel, the Landsat pixel. This is 30 meter. So we've been working with them, and one graduate student is coming at the end of May. So keep continuing on this data from Chile. Turkey, I did work with some of the people at Turkey. Again, there's water conflicts in the country. There's that Tigris, Euphrates River. This mouse is really hard to move here. Okay, I can find it here. All right. And I selected a region. I have a in-progress proposal to Turkey, DSI, the State of Hydraulics Engineering. They were really interested in having an ET maps. Again, the water, is an issue, especially from these Tigris and Euphrates. There's always pressure. There's, between Syria and Iraq and Turkey. If Turkey uses more water, there's not much downstream user in Syria and Iraq. So this is a really hot spot that I figured I should just go ahead and bring it to their attention. So I processed that image. Here's this Atatürk Dam, and the fight really started after 1990. Turkey built that Atatürk, the biggest, I think the third biggest dam in the country, here in the region. So they converted most of these dry land to irrigated agriculture. I believe this was a June image. I processed a number of images. Here's the Harran Plain. Right now it's completely irrigated agriculture. So there's less water going to Syria from the Euphrates now. And you can see that, it's just that the water is being used by the irrigated agriculture. And again, it's a critical region. 80% of cotton production comes from this part. There's an ET map. Again, you see the rangeland. Again, Turkey was a little difficult to work. Look at that complex terrain. I had to use the mountain model so that we do better job with north-facing, south-facing slope, the radiation, estimation. Here's the ETRF. The ET, so we can really see the ET in June from these irrigated Harran plains. No wonder there's complaint from the Syria. So the next application is Google Earth Engine. We've been working with the University of Idaho and again, Nevada, DRI to really create a clone or version of metric, a so-called eFlux, Earth Engine Evapotranspiration flux on Google Earth Engine. It's really cloud-based processing. Whole idea is make these images available, to the entire planet free, just like the Landsat images free. All right, here's we've been working, with both universities, and here's a code that Babu has been working on at least for the last 6-8 months, coding Python, using Python, JavaScript to run this eFlux on the Earth Engine. Again, those who knows programming, they don't even have else. What if, just a lot of stuff has been dropped from their library, so you have to really, get familiar with their libraries, the codes in Earth Engine. So, and here's just some application. Right now, we have, let's say, 3 phases. First phase, the product is produce ET for the instantaneous. Every time and there's a satellite pass, after USGA, Google puts that in their archive, collects them. And so we would like to able to have the capability to process this. And right now, that's where we are. For Kanos, we're processing these instantaneous ET maps. Later on, the challenge comes in when that seasonal monthly maps and clouds, dealing with clouds. So this project might take, a few years, at least another couple years. We'll see how it goes. Here is, for instance, an ET map for that Palo Verde, California area. Here's the beautiful center pivot fields, clay centers. Again, here you can see the fields. And when you zoom in, this is doing the calculations on the fly, and you can save the data. You can see the variation from field to field and produce the ET for the instantaneous image. I'm gonna paste these demos. So we needed a reference ET map, kind of to fill in between the Landsat overpasses, and this is up running at the Google Earth engine. We have the daily reference ET map running, going back to 1951, producing reference ET at the 12-kilometer spatial resolution. Again, it's using FAO, Penman-Monty, FAO 56 Penman-Monty technique. Let's see. Oh, I wonder whether I have a slideshow here too. Maybe okay. All right. The next project for the Google that I got funding, this is independent and the other universities, is really develop an app. Eventually, I'd like to see us developing an app that we can use in Apple phones or iPhones or the smartphones. We're going to be using, we're very early in the stage here. There's a PhD student, Yao, he's working on this. We're going to use NAPE high-resolution aerial data to map the greenness, the lawns for residential areas, and then converted the vegetation indices and resulting crop coefficient, and using reference to crop coefficient approach. We're going to provide homeowners with the gallons of water per day. How much water they need to apply to irrigate their lawn. After I start getting 400 water bills in summer for my house, I figure there's something wrong. Either I need to do some testing. It's just too much water. I think we can do a better job. And I didn't know it was, especially July. It was hot. Sometimes you ran that irrigation system probably longer than what you need. So this is how it originated, really helping the homeowners, to apply the amount that is needed to keep the lawn green. And we're going to be utilizing a lot of things that we developed, like those reference ET maps from the previous project. Again, eventually this will be an app that is, you can run it. We're very early on this one. The efflux were almost, more than halfway. This one, we're pretty early in the phase, but it's going to be a nice, useful tools for the cities. Cities, they need to reduce the residential water use. They have to do a better job managing the water resources, especially with these droughts. Again, this is a new project that just got funded about 2 months ago from NASA's architecture team. It takes 4 years to build the satellite. Sometime this summer, they need to start building Landsat 9, if the Congress approves. So, again, I told you, they are not reluctant. It's a lot of money. NASA wants to use that funding for other science mission. The Landsat. What is Landsat for? They don't really appreciate the value of the Landsat. So they were interested in, what if we put these 2 sensors onto satellites? With just putting both thermal and the shortwave is too expensive. It's going to be cheaper, if we just put a small set where this thermal sensor is there. Or can't you guys just use the data from the Sentinel, the European satellite? The European satellite doesn't have the thermal band. They have the shortwave. why don't we just launch a small sat that we're going to give you the thermal, but you're going to use the data from the European satellite. So just as, it comes down to all, the budget, how much money we can save. And one question they had is, how large can the thermal pixel size can be, so that, we don't lose accuracy in ET when we look at the individual fields. For instance, the Landsat 7, we had the 60 meter, the pixel size. Again, we're all talking about thermal. Thermal is the one in the discussion. And so the Landsat 8 is 100 meter, should we make it 60 or 100? Just 120 or 360? How good is the 60 meter versus 100 meter? So we had to do a number of, analysis so that we can come up, with the right pixel, with the optimum pixel size for thermal band for Landsat 9 and beyond. So we did both ring analysis and transect analysis. Again, we utilized this UNDERFLY the data from California. That's been a very useful data because we had two satellites, collecting data at the same time simultaneously. And then they have some other question, the water resources community want every, 4 day, they want, data. And then the surface temperature, how accurate should it be? Can you handle the bias, 5 degree? Or, does it have to be really precise? Let's say, just a lot of questions that they had, and then this architecture team. Anyway, so there's just to focus on this question number 1. What is the optimum pixel size for thermal band, for the lengths, Landsat 9 or beyond? So we really eliminated a lot of fields. Look at these uniform fields and created transects and ring. Then we assume that you really see the contamination in the thermal band at the field H. If this is, I think I have a better slide here. For instance, here is the pixel size for Landsat 8, 100 meter. Here's the pixel size for Landsat 7. So if there is a road here or some building, something else, rangeland, here we have one number for these 100 meters. And if this pixel moves a little further, there will be contamination. So we were, assuming that there will be more of these, in the field edges, and that's where we start drawing these transects and the rings. Anyway, here's the kind of the results that we were expecting and found that, this is the distance. These are the rings. Ring 1, this 30 meter, you go further from the field edge. There might be some roads, some buildings, there might be some contamination in the thermal pixel. And so here really, when you look at the data here, and this is the distance, the closer the lines, that means there is less variation. Let's look at the ring 1 again so that we can understand this. Ring 1, that's my core here, the corner, the edge of my field, the 30 meter, this area. And we see a lot of variation. These are individual fields. A lot of variation in ET versus, for Landsat 8. Again, we don't like that 100 meter, and then we see that the impact of that 100 meter. There's a lot of contamination. And, that is why the ET is changing, quite a bit for this ring. Again, here this is the nice pad that we had data from both satellites at the same time. We did a comparison with 7 and 8. We like 7. If everything is uniform, if this is straight line, give me that. It's gorgeous, beautiful, no variation, no contamination. Again, the larger you go in this pixel size, you're going to introduce more contamination from adjacent areas. And then you can have a field ET, for instance, or anything you do at the field level. So here, kind of, these are the several fields, kind of having a mean. Landsat 8, Landsat 7. What we found is, the ring 2, the Landsat 7 can tolerate ring 2. The 60 meter, when you have 60 meter, you have less contamination in thermal band. But the Landsat 8, there's more contamination. So it's just getting worse. Our ET is suffering. So we can't really see the ET, from individual fields. We are losing the definition of the fields. Right, my next slides again. So that means that smaller pixels, we're gonna deliver these products by the end of March. And, what we found is that this is just a snapshot. The smaller pixels means, the more accurate ET. And again, right after you pass that 60 meter resolution, that is where you're gonna lose the integrity of the field level ET from the thermal band. Another question that NASA, again, raised, Doruk Öztürk, my graduate student, has been working day and night over this. Again, getting this shortwave data from Sentinel European satellite, or getting, or having sensors into two satellites. What if we launch a small sat? We give you guys thermal band. Can you is it good enough? Do you need another band, another shortwave band? So, here, and, again, the Landsat means, the cloud. You have all these clouds that you have to mitigate, you have to deal with. So, what if we have on the thermal band? Can we identify, is it good enough to identify the cloud and shadow? Am I gonna get right, accurate energy balance parameters? And no, the thermal wasn't enough. What we found out, again, we don't have conclusive results for this. What we found out is the near infrared, we really need a shortwave band to help us to identify the clouds and shadows. We also found that for more humid region, you have the fog and haze, and you have this different type of clouds. We found that the blue band is being more useful too. Again, these are not conclusive. We have 3 more weeks to finalize these results. Another question by NASA. So far, up to Landsat 8, everything, all the data is being stored at 8-bit. You have all these blocks, 0, 1, 0, 1, 0, 1 numbers, and the data is being stored. So with this state-of-art Landsat 8 has the 12-bit. Well, it saves money. It saves, time. If, is it good enough, the 8-bit? Do we need 12-bit radiometric accuracy for the next satellite? So here is showing a 12-bit versus 8-bit. We gotta again crunch the numbers. And it took for 2-3 weeks for us. How are we gonna do this? So here's a 12-bit. What's a 12-bit? That's 4096. So your temperature is, let's say 306, the temperature of your pixel field. So you're gonna express digital numbers ranging from 0 to 4006, to express that temperature with the digital number. So when you have this 12-bit, look at the area here. You can really see the transition from the low light blue to higher blue. Here you have just chunk, when you have that 8-bit, there's jump. So, and then going over here, you can really see different shadows. Let's say that this is your temperature. This could be your 280.5, 280.9, or 289. It's just that, now you have 12-bit to store that data. It's just much more precision to store that temperature. Well, how important is that? I give you a thermometer and, 2 thermometer, and you measure your temperature. And one is giving you 96, 97, 98. Another one is giving you 96.1, 90. You can have the decimals. So it's the same question or phenomena here. How accurate, this temperature data should be, and what's the radiometric accuracy do you need? Do you really need that 12-bit? Do you really need to read your temperature, your body temperature with such detail? So, we're trying to answer this question. Again, the 8-bit because just is much more simpler. And so, just that there's a lot of jumping. Maybe that there is a range in that temperature, in that pixel, but that's being buried, or it's being kind of, just that either a low or upper number is being interpolated. All right, here, this is again similar to what I'm saying. Surface temperature, 12-bit system. You have the surface temperature 8-bit. So here, for instance, that pixel, the temperature is ranging from 280 to 282. Versus when you have this 8-bit sensor collecting data for all these numbers, you have the same temperature. So you might have, more than 2-degree Kelvin error in your temperature just because of this radiometric accuracy of this thermal data. So again, these are a lot of information, and there's some more revisit time. So we're trying to do our best to resolve some of these issues so that we can help, give some guidance on thermal imagery for the Landsat satellite. All right, I guess I'll end my presentation here. Again, I want to make sure that here's the message, we need Nebraska's support so that we're going to see more satellites. The sustainability of this Landsat depends on, you guys sitting down here. If we don't tell them that we need this, we're going to suffer. We're going to pay. We're using this data to manage our aquifers, our groundwater, surface water. And then we would like to see them, putting more of this. This is a great, gorgeous, beautiful, fine resolution data set that we can give as a gift to our kids, grandkids. So hopefully our senators are gonna, put pressure, the Congress, support this effort. All right, thank you. Appreciate it.
Very nice presentation, Ayse. I really enjoy it. I have a question. Is regarding what we have from satellites are practically radiation, right? And we use this information and we put it somewhere so we can get the estimates of ET. I wonder if that's somewhere where we put the radiation in order to get these estimates, introduce errors or introduce uncertainties.
Mm-hmm.
What is the contribution of this expression or the parameters used in this expression to the estimates of ET? If you compare or as a pattern of comparison or something to compare with, what is your speculation or your assessment about what satellites produce with what is produced by models, for example?
Well, let me rephrase your question and make sure that I understood correctly, Francisca. What you're saying is that what's the accuracy of these ET data from the satellite that we get? Is that what you're saying?
Thank you. Basically, is what would be the uncertainty of these estimates, and where could you allocate this uncertainty? Where is the point or the expression where this uncertainty may be important, or the source of this uncertainty is located?
Well, we solved the radiation, the ET is a residual in energy balance. That means you take that radiation, use it, some of them to heat the ground, some of them to heat the atmosphere as H, the rest is being used as ET. And in metric, we're using this anchor pixels here in the model. We're telling that, a hot and a cold pixel, hey, you're my cold pixel. You're going to evaporate as much as potential ET. Then, we're telling the hot pixel that, you're going to be, my almost zero ET or whatever from the soil-water balance. So I think the model is doing a pretty good job estimating ET, but because this is inverse calibration, we know exactly what's that actuality for our calibration points. And then, we're doing inverse calculation to find the rest of pixels. So the ET is we have maybe less than 5% uncertainty, I would say, overall. But when you look at the sensible heat or the ground heat flux, the error might be as much as 50%. I don't care, though. I'm saying all I need is ET. Okay, here's my, potential ET. Here's my dry spot. And give me, in terms of fraction of reference in T, in between using the energy balance. So we're good. Whatever the error, we're just throwing into, for instance, sensible heat flux. I hope that helps, and I know there are some audiences here who can help with that question too. Is that answers your question? Again, I think the ET estimate, we're really good with our ET predictions. Again, your measurements, you get that closure error in eddy, 20% minimum. So I think on average seasonal 5 to 10% in, ET. But again, the uncertainty, the error is, pretty high or is not as good, when you go to sensible heat flux, because we're throwing everything, throwing bias in those so that we do a good job for simulating ET. We're interested in ET. Does that answer your question?
Another question?
First of all, thank you for your presentation. It was really interesting. Time is the essence in a lot of the management and compliance. So I was interested in your comments about your instantaneous ET maps or on-the-fly imaging. How quickly can you convert the flight or the photograph to real ET data for a given area?
You mean right now? I think that's the beauty of running this Google Earth engine too. It's taking us seconds for us to process instantaneous image. If I remember correctly, right after 30 minutes, the satellite pays. The data is available for user. So it can be as quickly. And then with the Earth engine, with this cloud computing, we're spending days, even with workstation, to process. Now it's only less than 5 seconds. We're getting the instantaneous number. So hopefully we're going to get there. As soon as we get the image, we're going to make that data available to user.
Thank you, Dr. Kilic.
Thanks.